Good morning, my name is Talifhani Mushiana, a PhD student at the University of Science and Technology of China. Today I'll be presenting part of my PhD work that is titled Fossil Soldier Preparation of High-Entropy and Multielemental Electrocatalyst for Efficient Oxidation of Methanol and Urea. This is the outline of my presentation. With the rapid depletion of fossil fuel, researchers have started looking into other ways of generating electricity. And direct fuel cells have long been considered as a potential power conversion device that converts electrochemical energy into electrical energy and also valuable chemicals. This is all to their key advantages such as high energy density, great efficiency, environmental availability, quick refueling. It's easy to store and distribute. And the electricity generated from these devices is able to power phones, laptops, vehicles, and residentials. Now, various liquid fuels can be employed in direct fuel cells, including methanol, ethylene glycol, ethanol hydrogen, ammonia, hydrogen, urea solution, and other fuels. The liquid fuel is fed directly into the anode compartment, where the oxidation reaction takes place, and its performance depends on the efficiency of the oxidation reaction. And thus oxidation reactions are somehow kinetically sluggish due to multi-electron transfer processes, which necessitates the need to fabricate electrocatalysts to aid the sluggish kinetics of the reaction. High-entropy alloys are a new class of multi-elemental alloys that involves high mixing of 5 or more elements near equiatomic concentration, and the major effects or the core effects that differentiate those materials from traditional alloys includes high entropy, slow diffusion, lattice distortion, and cocktail effect. The system of these alloys possesses high degree of entropy compared to the conventional alloys, with advantageous properties such as corrosion-resistant chemical stability and improved catalytic activity. Their synergic effect carries unique properties which are expedient for catalytic oxidation reaction, and the catalytic activity of this material can be boosted by tuning the composition by combining more catalytic active elements, as well as tuning their phase structure either into intermetallic compounds, solid solutions, and amorphous phases, or combination of those phases. Amorphous phases, multi-elemental materials are significantly unexplored. However, their dissimilar elemental interaction could offer access to new arising properties. In this work, we used a soldier method to prepare the multi-elemental electrocatalyst, which soldier is one of the mainstream methods to produce multi-elemental materials and also permits charge distribution between different elements. The nickel, iron, cobalt, boron phosphate material was prepared by using a modified aqua soldier method using metal chlorides precursors, trimethyl borate as a precursor for boron, and phosphoric acid as a precursor for phosphate, and as well as an acid catalyst for hydrolysis and gelation processes. Now the precursors were added into a mixture of ethanol and water for hydrolysis to take place. After propylene oxide was added into the mixture, then the gel was formed in less than 5 minutes through the formation of metal-oxo-metal bonds, and the gel was allowed to age for 24 hours, then dried in air at room temperature, and a glass-like dense gel was formed. The morphology of the prepared catalyst material was analyzed using scanning electron microscopy (SEM) and transmission electron microscopy (TEM), and both images for SEM and TEM shows agglomerated nanoparticles forming porous network structures, and the STEM, performed in high angular dark field mode, showed wrinkled entwined porous nanostructure composed of nanoparticles, and EDS spectroscopy was used to determine the weight and atomic percentage as well as the distribution of the elements. Now, elemental mapping at the nanometer scale also indicate that the elements were uniformly distributed in the composite, and the X-ray pattern was also shows that the material prepared is an amorphous material. The electro-oxidation contrivance of the prepared catalyst was studied using cyclic photometry in 1 molar potassium hydroxide solution at 50 scan rate. The representative CV curves shown exhibited well-defined redox peaks during anodic and cathodic scan, corresponding to nickel 2 and nickel 3 redox pairs. And then by comparing the activity of the nickel phosphate and nickel phosphate boron, it can be seen that the redox peak increases after adding phosphorus to nickel catalyst and further increased after adding boron to the nickel phosphorus catalyst. And then the other one shows after the addition of cobalt and iron elements, shows that after adding cobalt, the overpotential shifted to the more negative side, and after adding iron to the nickel composite, the current density increased, and this shows that the addition of the iron and cobalt element changes the nickel surface properties as well as the kinetics of the surface, the electrolyte and intermediates interaction. Now, with nickel species being the most active sites of the catalyst, the onset potentials of the anodic scan of methanol and urea can be estimated to be close to that of nickel 2 and nickel 3 oxidation. Now, to validate, we also sought to calculate the surface coverage of the nickel redox species, and the surface coverage of nickel was calculated to be higher than those of reference catalysts, and also the Randall-Cubic equation was also used to determine the diffusion coefficient, and the proton diffusion coefficient of the prepared material was found to be much higher than those reported for nickel catalyst. Now, the higher diffusion coefficient value shows that the prepared catalyst facilitates the generation of more nickel oxyhydroxide species during the nickel redox process, and hence the negative onset potential and high current density. To evaluate the activity of the prepared catalyst for methanol and urea oxidation reaction, CV measurements were performed in potassium hydroxide with either methanol or urea at a scan rate of 50 and linear square wave voltammetry at the scan rate of 10. And the prepared electrocatalyst shows electrocatalytic activity in methanol oxidation presented the highest MOR activity compared to the reference catalyst in terms of specific activity, and this can be attributed to the provision of more accessible active sites and the synergetic effect of the multi-elemental material that improves MOR. Now, electrochemical impedance spectroscopy measurements were also conducted to gain insights on the electrode kinetics of the appraised catalyst for methanol oxidation, evaluating the charge transfer resistance between the modified electrode and the solution, and also the linear square wave were measured at a scan rate of 10, demonstrating the lowest potential for MOR compared to that of OER, with a potential difference of about 20 millivolts, and also the Tafel slope was about 120 for MOR and 217 for OER, where the lower Tafel slope value for MOR implies a faster reaction kinetic for MOR than that of OER, which indicate the good specificity of the prepared catalyst for methanol oxidation reactions. And the similar work was also done for urea oxidation reaction and portrayed a similar trend to that of MOR in terms of the onset potential and current density. The chronoamperometric CA and chronopotentiometric CP tests were conducted to study the durability of the nickel iron cobalt boron phosphide catalyst for both MOR and UOR, and notably the chronoamperometry profiles depict fast drop of current density at the beginning of the reaction from 87 to 84, and this is broadly conferred in most MOR and UOR studies. And for MOR, the catalyst was able to retain about 95.7 of its initial current density after 1 hour CA test, and conversely for chronopotentiometry test, it showed that to maintain a current density of 87 milliamperes for an hour, an additional potential of about 0.2 volts was required, and the same test was done for urea oxidation reaction, and after 6 hours the CA test, the catalyst retained current density of about 66.5 milliamperes, which is 85% of its initial current. And for CP also showed that to maintain the current density of 75 milliamperes for urea oxidation reaction for 6 hours, an additional potential of about 0.8 volts is required. And then CV was cycles 500 cycles were also conducted to study the stability of the catalyst. As you can see, for both MOR and UOR, the catalyst shows remarkable stability. For electrochemical conversion of methanol to formate, we identify the product after long-time electrolysis of 24 hours at 1.56 volts RHE, and the electrolyte was sampled and monitored with NMR at different times during the test. And also the carbon NMR spectra depicts two chemical shifts, which are representatives of formate and carbonate, and also the HNMR shows the chemical shift of formate at 8.3 ppm. The formate yield increased from 13 to 19, and after 19 hours it then decreased. This could be that the formate was then now converted into carbonate, which suppresses the further accumulation of formate. And as you can see, it's much visible on the carbon spectra. And also the Faradaic efficiency of MOR was estimated to be 91% after 19-hour electrolysis, which is among the highest Faradaic efficiency of the reported electrocatalysts for MOR. Thus, the used electrolytes can be recovered through membrane separation technique and produce formic acids as valuable added chemical. This work presented a simple strategy to prepare low-cost electrocatalysts, and also that with nickel as a primary active components for MR and UR, the addition of cobalt can efficiently reduce the overpotential, while the addition of iron can significantly increase the catalytic activity and durability. And high performance multi-elemental electrocatalysts for energy conversion and production of value-added chemicals. I would like to thank the following, and thank you for listening.